Today we're going to be talking about logarithmic functions, which you should be thinking of as undoing exponential functions and being their inverse. And what do I mean by that? So for example, if you have the function f of x is equal to x cubed, you hopefully think the reverse of that would be cube rooting x. So in the same way that if I had that, in this case, f of 3 is equal to 3 cubed, that means that the inverse function, which f3 cubed is 27, that means the inverse function evaluated at 27, the cube root of 27 is 3. So our x and y's flip-flop between the two. If on f of x is 3 cubed, I have the point 327. On f inverse of x is the cube root of x, so if I'm evaluating at 27, the cube root of 27 being 3, I have the point 27, 3. Think the same thing with exponents and logarithms. So if I have a function g of x is equal to 3 to the x, that means his inverse is going to be log base 3 of x. So if, for example, I wanted to evaluate the original function at 2, that would be 3 squared, which gives us 9. That means the original function has the point 2, 9. The inverse function, the logarithm evaluated at 9, is log base 3 of 9 to give us 2. So then we have the point 9, 2. And there's a couple different ways to think about logarithms. If you feel really comfortable with inverses, though, that is the most straightforward way to think about logarithms. So I would always think, well, I know if I'm given log base 3 of x, that's the inverse of 3 to the x. Let me find some points on 3 to the x, flip-flop x and y, and boom, I have my logarithmic function. We're going to go over a couple different ways to think about logarithms today, but the fact that they are the inverse of exponents is something I always want kind of lurking in the back of your mind. And even though we're not going to go over how to solve logarithmic equations just yet, or exponential equations that are a little bit spicy just yet, we will eventually be able to sort of do the move that they also undo each other. So in the same way that if I take the cube root of x and then I cube it and I sort of say that cancels out and leaves me with just x, I can actually think of kind of the same thing with logarithms and exponents, although we're not going to get there quite yet. That if I have log base 3 of 3 to the x, I sort of think that undoes each other. I'm just left with x. And I can also think 3 to the log base 3 of x, that sort of undoes each other, and I'm just left with x. This is not a move we're going to really do much today, but we'll be doing it soon. And again, just kind of really think about logarithms sort of like the cube root equivalent for an exponent. They undo a function we're really familiar with, exponential functions, and they are the inverse by definition. But with that extended intro, as always, feel free to jump to a particular point in this video if that's what works best for you. And let's kind of get more into the nitty-gritty. So as I mentioned, exponents and logs by definition are inverses. And that we have the same sort of rules in terms of what's allowed to be in the base of a log as we do on an exponent. So it has to be bigger than 0 and it cannot be equal to 1. So if, for example, f of x is equal to 2 to the x, that means the inverse function is log base 2 of x. So we keep the base the same, and then we end up flipping our inputs and outputs. And that's exactly how we're going to convert between logs and exponents. So regardless of which way you're converting, you should be thinking the same base to the output equals the input. I hesitate to say x and y because sometimes they may flip the location of x and y. As you sort of notice with this b to the y equals x, we kind of flipped the normal location of it. But you should be thinking whatever way I'm converting, keep the base the same, then raise it to the output or put the output inside the log, equals the original input. So let's see that in action. So if, for example, I have y equals log base b of x, I'm going to keep the base the same, which is b. B here is the base. To the output, in this case my output is y because it's on the other side of the equal sign, equals the input x. That's exactly what we got here. And it works the other way around. Let's say I was given this and I wanted to rewrite it as a log. So then I would do log of the same base b of the output, in this case the output is labeled as x, is equal to the input, in this case labeled as y. And the fact that these guys are inverses really tells us a lot about the domain and range of a log, because it's not necessarily something I could think of straightforwardly, super easily, since whatever is inside the log, you're asking yourself, this base to what power will give me what's here on the inside, and that gives you the result. But if I know how exponents work, which hopefully I do, the domain of an exponent is all real numbers. The range of an exponent, if it hasn't been transformed, is 0 to infinity, because if I'm taking some positive number that's not 1 to a power, I'm always going to end up with a result that is strictly positive. That means that on the log function, the domain becomes the range, so the range is now negative infinity to infinity, and the range becomes the domain, which is 0 to infinity. So if I'm converting between logs and exponents, again, always think same base to the output equals the input. So for example, if I have log base 2 of 8 is equal to something, I'm just going to put an equals y. That means same base 2 to the output y is equal to the input 8. And 2 to the what does give me 8? That would be 3. So that would be your answer. Same deal here. So if I have 10 to the 5th, well, 10 to the first is just 10, 10 to the second is 100, 10 to the third is 1,000, 10 to the fourth is 10,000, and 10 to the fifth is 100,000. We just actually add on 5 zeros right there after the 10. To convert this to a logarithm, I do log of the same base 10 of the output 100,000 equals the input 5. So I've just told myself 10 to what power gives me 100,000? 5. And I just figured that out. Go ahead and pause your video and see if you can convert these exponents to their equivalent logarithmic form. So remember 2 to the third is equal to 8, because that means 2 times another 2, which gives us 8. And then I do log of the same base of the output, in this case 8, is equal to the input, in this case 2. 10 to the negative 4, keep in mind that's the same thing as 1 over 10 to the fourth, because the negative becomes the denominator of a fraction. We end up doing the reciprocal and then changing that exponent to positive. And then 10 to the fourth becomes 10 to the first would just be 10, 10 to the second is 100, 10 to the third is 1,000, 10 to the fourth is 10,000. You may have equivalently thought more of a scientific notation way, where you say, okay, I'm going to move this decimal 1, 2, 3, 4 times. You could have also done that as well, and that would have been fine. Either way you sort of wanted to think of it. Regardless, we end up getting, also when I move that decimal that many number of times, I always sort of, there should have been 1, 2, 3, 4. We should have ended up with 3 zeros in front of that 1. 1 over 10,000 gives us 0.0001, because the first place is the tenths place, then we have the hundredths place, then we have the thousandths place, and then we have the 10,000th place, is how that works. Okay. Regardless, yeah, shortcuts are no good. Shortcuts always lead to messing up. I actually think in terms of logic-wise, negative exponent moves to the denominator 1 over 10,000. Or if you're thinking about what its decimal equivalent is, we know how place value works. First place is 10th place, second place is 100th place, third place is 1,000th place, last place is 10,000th place. Anyway, sidetracking because that's not the main point. The main point is that we just figured out that 10 to the negative 4 is equal to 1 over 10,000. So then we can go ahead and convert that to its log. So that would be log same base 10 of the output 1 over 10,000 is equal to the input, negative 4. So the result can be a negative now, but whatever we put inside the log better be a positive. Otherwise, if I was saying log base 10 of negative 2, that would make no sense. There's no way I can multiply a positive by itself any number of times and get a negative. Go ahead and pause your video and see if you can convert the other way around. So here I may not actually know the answer just yet, but that's okay. So I do same base to the output, in this case y, is equal to the input, in this case 9. So that means that output, 3 to what power gives me 9? Better be 2. Same deal here. And go ahead and convert. So we say same base to the output is equal to the input. So in this case, 5 times itself, how many times gives me 125? Well, 5 times itself twice. 5 times 5 is 25, times yet another 5 is 125, so the answer is 3. We can do the same thing with something just a little bit spicier as well, so go ahead and pause your video and see if you can figure these guys out. So we're going to put in some sort of dummy variable for the answer. Then we say same base to the output is equal to the input. Then it may be helpful to go ahead and convert that the square root of 6 we know is the same thing as 6 to the 1/2 power. So now we have figured out that that must have been 1/2, because if 6 to the something is equal to 6 to the 1/2, then that something better be a half. Same deal here, so we say same base to the output is equal to the input, in this case 1 million. So that would be, in this case, 10 to the 1st, 2nd, 3rd, 4th, 5th, 6th power. So we must have had 6. Go ahead and pause your video and see if you can do these two. First step for both of these is you want to convert them to exponents. So we have same base to the output is equal to the input. And then I'm going to actually just go ahead and try to convert 3 to what power would be 1 over 27. So 3 to the 3rd would give me 27. And then if he's a fraction, it must have been 3 to the -3 to give me 1 over 27. So it must be that this is equal to -3. If you weren't quite sure how to approach this, and now this gave you a little bit more of a hint, go ahead and pause again to do this next one. Otherwise, we'll just keep going and comparing our answers. So here we first convert it to an exponent. That's 2 to the y is equal to 1 over 32. Then I want to convert 1 over 32 to the 2 to the something. So that's 2 to the 5th would give us 32, right? Because 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times another 2 is 32. And then to make him a fraction, it must have been -5. So we end up with an answer of -5. Sometimes there's a little bit of shorthand given to really commonly used logarithms. In particular, log base 10 is oftentimes just noted as plain old log. And log base e, since e is such a special number and it's used so often, it's actually dubbed the natural logarithm, and it's labeled as an ln for natural log. For the domain of a logarithm, we again want to be thinking about the fact we know it's an inverse exponent, and we know on exponents the range is never smaller than 0, so the domain on a log is that whatever's inside the log has to be strictly bigger than 0. So in order to do this, log base anything, whatever is that something, you're going to set up an inequality, set in bigger than 0, and solve. So on this one, even though there's a whole bunch of stuff going on outside the log, that doesn't actually matter for the domain. For the domain, I just care whatever is inside the log better be bigger than 0. So in this case, no more solving needed. It's from 0 to infinity. Same deal here. Regardless of what this base is, regardless of what's going on outside the log, what I care about is whatever is inside the log better be bigger than 0. So I go from 0 to infinity as my final answer there. For these two, I have something a little bit spicier going on inside the log, so I have to do a little bit of work. So in particular, I need to set up that x plus 3 has to be bigger than 0. Take away 3, take away 3. So x has to be bigger than -3. So from -3 to infinity is what the domain on this log is. Same deal here. I want to set up a little inequality. So x minus 2 has to be bigger than 0. Undo subtracting 2 by adding 2 on both sides. X better be bigger than 2. So from +2 to infinity is the domain on that log. Once we get into how to solve like quadratic inequalities and rational inequalities later, you'll see that appear in future homeworks that we're going to come back to this idea that you have to set up the inequality that whatever's inside the log has to be bigger than 0. So in order to graph a log, we can always think about the fact that it's an inverse exponent. And in particular, that reveals two really key points that have to exist on it. Because if this log is an inverse exponent, so for the function b to the x equals something, we know any base to the 0th power is 1. So if 0, 1 exists on the exponent, then 1, 0 has to exist on any sort of basic log graph that hasn't been shifted left and right. And similarly, if I take anything to the first power, that gives me itself. So if 1 comma the base exists on the exponent graph, that means the base comma 1 has to exist on the log graph. And that's why that is noted here. You'll also notice that ends up facing opposite directions, depending on whether or not we have a base that is a fraction, so that's sort of dealing with that negative exponent that has been reflected over that y-axis versus just a larger base. But let's actually take a look at some examples. Another thing that may be worth noting is here, as your base gets bigger, so like natural log is secretly base e, log by itself is secretly base 10, it sort of flattens out towards the x-axis because now you're going to be having to, like for example with log base 10, if I ask log base 10 of 10, well that's saying 10 to what power gives me 10, that's just going to be 1. So I haven't even like moved up that much. Versus if I'm asking log base 2 of 10, well that's not something particularly even because I can't think of 2 to any even power that gives me 10. But 2 to the 3rd is 8 and 2 to the 4th is 16, so that would be somewhere in between 3 and 4 as its answer. So you would end up with something like 2 comma 3 point something, 10 comma 3 point something versus 10 comma 1. So that's why it sort of flattens out, because you're now having to deal with bigger and bigger x values for smaller and smaller y's essentially. So this is sort of the mental image that you should have, that we should be getting flatter and flatter and flatter closer to that x-axis as that log base gets bigger. Now, all those mental images aside, you might be like, okay, I just want to know how to solve the problem. Great, we're going over how to solve the problem. So in particular, things are nice because we have a one-to-one function, so we can always think in terms of the exponent. In the same way that an exponential graph had a horizontal asymptote at y equals 0, that flips for a logarithmic graph having a vertical asymptote at x equals 0, dealing with that domain where we can never quite hit 0, but we are allowed to hit numbers that are arbitrarily close to 0, such as 0.0001, something like that. For the range, that's negative infinity to infinity, because we're going over to negative infinity down and positive infinity up in both directions. And the fact that we have these two key points, 1, 0 and base, 1, ends up being super, super helpful. And again, that comes from the fact that this is an inverse exponent. So if 0, 1 exists on exponents, 1, 0 exists on y's. If 1, base exists on exponent, base, 1 exists on y's. There is no y-intercept because I'm never allowed to equal 0 for x. So I can't plug in x and 0 and get a y-intercept. Not allowed. Unless you've shifted your log function left and right. And it's going to look like this, increasing as long as the base is bigger than 1. It's going to end up reflecting over that x-axis if it's a base in between 0 and 1, and that again comes from the fact that if I have something like 1/2 to the x, that's the same thing as 2 to the negative x. So you've effectively originally reflected that over the y-axis when you're dealing with the exponent, so that becomes reflecting over the x-axis when dealing with the logs, because you've inverted x and y for logs and exponents. And again, this is the image you should be having, that because it's an inverse exponent, I've flip-flopped the location of x and y everywhere. So 0, 1, became 1, 0, for example. 1, 2 became 2, 1. If we have over here 2, 4, that's going to become 4, 2. It's always the mental image you should be having. And that is one way that you can graph logarithmic functions if you're like, I like knowing the logic and not necessarily like memorizing a set of points. Great, you can do that. Look at the points that are on its inverse, flip the x and y coordinates, and now you have the log. So let's go ahead and take an example of that with 2, for example. So here, on the inverse function 2 to the x, well, 2 to the negative 3 is 1 over 2 cubed, which is 1/8. So that means on the log function, I have the point 1/8 comma negative 3. 2 to the negative 2 is 1 over 2 squared, which becomes 1 over 4. So on the log, I have 1/4 comma negative 2. 2 to the negative 1 becomes 1 over 2 to the first, which is 1/2. So on the log, I have 1/2 comma negative 1. 2 to the 0 becomes 1. So on the log, I have the point 1, 0, which this ends up being a really, really nice key point to know. On the inverse, when I plug in 1, 2 to the first is 2, so I have the point 2 comma 1, which is also another really nice key point to know. 2 squared is 4, so I also have the point 4 comma 2. 2 to the third is 8, so I also have the point 8 comma 3. So if I'm plotting this, we got ourselves 1, 0, 2, 1, 4, 2, 8 3's off the page. And all these other guys down here are sort of these arbitrarily decreasing numbers as we get to like fractions. So like 1/2 is closer to 1 and it's a negative 1. 1/4 is a little bit further away from 1 and closer to the 0, and that's a negative 2. 1/8 is even closer to the 0, and that's a negative 3. So we can already see visually this vertical asymptote at x equals 0. And then we can connect these points to make our nice, beautiful logarithmic function. Another way, if you don't want to formally make the table that you can graph this, is if you know the point 1, 0 and the point base comma 1, and think about any transformations that might have happened to them, and you know the vertical asymptote x equals 0, great, you can go ahead and solve that. I probably should have also explicitly noted the domain and range here. My bad. So the domain you can see visually is from 0 to infinity, and the range is just from negative infinity to infinity. You also could have formally solved the x has to be bigger than 0, whatever you plugged into the log to get that domain. So that could have been what we did here too. We could have known the point 1, 0. We could have known the point base comma 1, which in this case is 2, 1. And then we could have known that there is a vertical asymptote at x equals 0. So I can plot that vertical asymptote at x equals 0. We have 1, 0. We have 2, 1. And that becomes our nice, beautiful graph. Go ahead and pause your video and try either method to try to graph the function f of x log base 5 of x. So in this case, I can think through the same sort of thing. We have the point 1, 0. We have the point 5, 1. If you had formally made the table, hopefully you figured that out too. And then we also have the vertical asymptote at x equals 0. So I can plot x equals 0 using that dashed line for the vertical asymptote. That's really a reference for me. It doesn't literally exist on the graph. Then we have 1, 0, 5, 1, and then we connect it in the shape of a log. Now the benefit of not doing this method is you better know what the rest of the shape of the log should be if you actually plug in other points. But as long as you're comfortable with the shape of the log, you're okay doing this. I can also use my knowledge of transformations to graph logs as well, so let's think through some of those. So in particular, the most consequential one will be if I have any sort of left-right shifts. And any left-right shifts are going to shift those x values. So in particular here, if I wanted to shift the x value, just like we always think with any sort of left-right horizontal shifts, you're always going to be shifting in the opposite sign. So if, for example, I have log base b of x minus 2, that means that we're moving to the right 2, versus log base b of x plus 3, that means that we're moving to the left 3. So in particular, whenever you are moving left and right shifts, you want to be moving the x value on all of your points, and that means you also want to move the vertical asymptote. This is the only type of shift that also shifts the vertical asymptote. So without further ado, let's do that as an example. So on the on log base 3 of x, remember we have the points 1, 0, and then we also have the point 3, 1. So 1, 0, and then base, 1. And then we normally have a vertical asymptote at x equals 0. So now that we have this new function, log base 3 of x minus 2, what kind of shift is this, first of all? That is a shift right to 2. So we want to move all of our x values right 2. So in particular, 1, 0 is going to move to 3, 0, 3, 1 is going to move to 5, 1, and x equals 0 is going to move to x equals 2. And that's exactly what we're going to draw. So we're going to draw our vertical asymptote here at x equals 2. We're going to have a point at 3, 0 and a point at 5, 1. Or if you want to formally make the table and shift more points, you could have done that as well, which would have again cued you to the overall shape of the graph. What would be our new domain and range then? So for our new domain, notice we never go left of the line x equals 2. So it's from 2 to infinity, with a parenthesis on the 2 to indicate we cannot equal 2 itself. And then for the range, that is negative infinity to infinity, because that has not changed. In fact, the range will never change with any of these transformations. We can also vertically shift logarithmic functions, and if that's going to happen, then just like with any other time we do a vertical shift, that will be adding and subtracting something on the outside, and that will be the same sign and same direction as the shift. So if we add, that means we move up, and we move those y values up. If we subtract, that means we move down, and that we move those y values down. Shifting the vertical asymptote up and down doesn't really do much, keep in mind, because basically picture that we have infinite string and we move that infinite string down. It's still infinite in both directions. We haven't really done anything with the string. So moving already vertical line up and down doesn't do anything, or at least not anything interesting. Go ahead and pause your video and go ahead and see if you can go plot this yourself. So remember, on the original here, we're going to have the points 1, 0 and 3, 1, which you either can know from knowing that 1, 0 and base, 1 are points, or you could have formally made your table. And we have a vertical asymptote at x equals 0. For our transformed function, what type of transformation is this? That moves down 2. So in particular, that now is going to change our y values. So 1, 0 moves to 1, negative 2. 3, 1 moves to 3, negative 1, and our vertical asymptote stays in the same place. So I'm still going to draw a vertical asymptote here at x equals 0, and then we're going to draw our points 1, negative 2, 3, negative 1, and then we're going to connect it in the shape of a log. If we're going to have any vertical stretches, apologies that this picture is the wrong picture. I will fix that on your version of the graph, but remember that's going to be having a number multiplied on the outside of the log, something on the outside here. So for example, 2 log base 3 of x would multiply all your y values by 2. Is sort of the internal image you want to have of any sort of vertical stretches, is that if it's a multiplication on the outside, that is multiplying those y values. And that's exactly what we're noting here. And in particular, you expect it to be compressed if you're multiplying by something that has an absolute value smaller than 1, and you expect it to be stretched if you're multiplying by something that has an absolute value bigger than 1. So for example here, we already kind of gave a little bit of a spoiler alert that if we have a 2 on the outside here, that means multiply the y values by 2. So in particular, if on the original log base 3 of x, you have the points 3, 1, 1, 0, and a vertical asymptote at x equals 0, well, 3, 1, we're going to keep the x the same, and then multiply 1 by 2, which gives us 2. For 1, 0, we keep the x the same, and when we multiply 0 by 2, that's actually still just 0. And that vertical asymptote similarly doesn't move. It still stays at x equals 0. So we have a vertical asymptote we're going to draw with a dashed line here at x equals 0. We're going to have a point here at 1, 0, and a point here at 3, 2. So it got vertically stretched up a bit, if you notice. For both this one and our previous one, since our vertical asymptote did not move, did our domain and range change at all? It did not. So for both of these, the domain is still 0 to infinity. The range is still negative infinity to infinity. You really only have to worry about the domain and range changing whenever you have any sort of left-right shift happening. So the domain here is still 0 to infinity, the range still negative infinity to infinity. Or if you end up reflecting over the y-axis as well, that would also change your domain. And these reflections are exactly what we're going to get into now. So the way that you reflect over the x-axis, like always, is where you multiply a negative on the outside of the function. That ends up flipping the signs on the y values. It's also called a vertical shift for that reason. To reflect about the y-axis, we multiply by a negative on the inside, and that flips the signs on the x values. And that actually would change the domain for that reason. Your vertical asymptote is at the same place, but now instead of being from 0 to infinity, you would now be from negative infinity to 0. So let's actually see that in practice. So go ahead and pause your video and see if you remember which type of reflection this should be and if you're able to plot it. So if on the original f of x is equal to log base 3 of x, we have the points 1, 0, 3, 1, and a vertical asymptote at x equals 0. Whenever we have this negative on the outside, that reflects over the x-axis, which is the same as a vertical reflection, which means we're flipping the sign on the y's. So for 1, 0, well, 0 doesn't have a sign. That's still going to be at 0. For 3, 1, that flips to 3, negative 1. For the vertical asymptote, that similarly actually does not move. So we'll note our vertical asymptote with a dashed line at x equals 0. Then we have a point at 1, 0. We have a point at 3, negative 1. And then we're actually going to draw it as a reflected over the x-axis shape. If you weren't certain about the shape, I would have encouraged you to go ahead and find a few more points, and you would have seen that the shape would have looked like that. Now, since we just did the previous transformation, you probably already have a good idea on what this should look like, but still go ahead and pause the video and see if you can do this transformation yourself. So if on the original log base 3 of x, we have the points 1, 0, 3, 1, and a vertical asymptote at x equals 0, we can go ahead and look at the transformed one. In this case, we have transformed him by reflecting over the y-axis, also known as a horizontal reflection. So that flips the sign on the x's. So 1, 0 transforms to negative 1, 0, and 3, 1 transforms to negative 3, 1. And our vertical asymptote, because 0 doesn't have a sign, actually stays the same. So we draw the same vertical asymptote, but the shape now is going to look a little different, because we're plotting now at negative 1, 0, negative 3, 1, and now we physically look like we have been reflected right over that y-axis. Go ahead and pause your video and think about the domain and range of each of these previous ones we just figured out. So for the function that had been reflected over the x-axis, that vertical reflection, the domain is from 0 to positive infinity, because that's how the x's are, and the range is still negative infinity to infinity. It reaches those heights at different locations now, but it's still, in the y's, ranges from negative infinity to infinity. When we reflect it over the y-axis, that looks a little different. Now our domain, the highest value is 0, and we're getting infinitely negative, so that goes from negative infinity to 0, but the range is still the same. We go from positive infinity to negative infinity. If you have more than one transformation, you want to do those transformations in order of operation. So you first do whatever is inside the log, then you do any multiplication outside the log, then you do any addition and subtraction outside the log. So go ahead and pause your video and do these series of transformations together. In terms of order of operations here, you want to do what's inside the log first, which is that we are shifting left 2, because that's inside the log and we want to use the opposite sign. Then we're going to end up reflecting over the x-axis, which in practice means we will flip the signs on the y values. And that's the order we want to do. So first thing we want to think about is just log base 3 of x, which we've been working with for a while now. So that would be at 1, 0, 3, 1. So 1, 0 always on the log function, base comma 1 also always on a basic log function, and a vertical asymptote at x equals 0. Then we want to think about just the transformation of shifting left 2. So negative 1, 0 shifted left 2 moves to negative 1. Positive 1, 0 shifted left 2 moves to negative 1, 0, because we do 1 minus 2 gives us negative 1. 3, 1 shifted left 2 moves to 1, 1, because 3 minus 2 gives us 1. And a vertical asymptote at x equals 0 shifted left 2 moves to x equals negative 2, since 0 minus 2 is negative 2. Then when we actually do our reflection, we are flipping the sign on those y values. So negative 1, 0. Well, 0 doesn't have a sign, so that is still at negative 1, 0. Positive 1, positive 1 shifts to positive 1, negative 1, because we want to flip the sign on that second one, the one that's corresponding to the y value. And that vertical asymptote does not change. So we end up with a vertical asymptote here at x equals negative 2. So that's exactly where we want to draw our dashed line. We now have a point at negative 1, 0 and 1, negative 1. And then we want to connect these in the shape of a log that has been reflected over the x-axis. If you weren't certain about this shape, I would have encouraged you to find additional points to see how that shape would have looked. To think about domain and range, since we did have a left-right shift, our domain did change. It is now from negative 2 to infinity, because now negative 2 is that vertical asymptote we're approaching, and the range is still from negative infinity to positive infinity. As always, I really encourage you to take a look at your textbook for even more examples and reach out to your instructor as well. Happy mathing!